Welcome back. We're beginning our module on exponential smoothing. So there will be about 4, maybe 5 videos on exponential smoothing. This one is going to cover the topic of simple exponential smoothing. Now, when I learned this, I learned it under the name the exponentially weighted moving average, or EWMA for short. And so some textbooks call it that rather than simple exponential smoothing or SES. I'm going to try to call it SES because that's the name of the function that the forecasting library uses for this. So let me begin by saying when SES is appropriate. And the answer to that is we're going to use it whenever there's a cycle present, but not a trend or seasonality. So the next video that I'm going to make is going to extend simple exponential smoothing to accommodate trends. Then the video after that is going to allow for trends as well as seasonality. So in this first module, we're only going to consider when there's a cyclical component to the time series. So one thing that I want to note is that all of our forecasting methods so far, we can think of them as weighted averages. Okay, so what do I mean by that? Well, our forecast, some number of periods in the future, given all the information I have as of time big T, is just going to be the sum of all my previous values with some weights. And these weights are going to have to sum to 1. So just to make things really clear on this, if you think about basic statistics, and in basic statistics, maybe we have, I'm going to go back to what the notation that you'd have in basic statistics. Let's say we've observed 4 numbers. And we want to find the mean of those. Our mean is just going to be x1 plus x2 plus x3 plus x4 divided by 4. And what I think is kind of important about this is you can think of this as really we're giving a weight to each of the numbers. So we multiply by the weight and add it up. And in the case of a simple mean, which is what we're doing here, the weights are always equal, and they're all equal to 1 over n, where n here is equal to 4. So you can think of this as the sum I equals 1 to n wi xi, and note that these weights always sum to 1. So the sum of the wi's have to equal 1. And the reason for that is it's going to give us an unbiased estimate of the true mean. So x bar is going to be an unbiased estimator of the true mean, which we would have called mu back in the basic stats class. All right, so here's the idea behind SES. So SES is kind of like a moving average, but we want to give more weight to recent observations versus observations that are in the distant past. So I think of them like a kernel smoother. So if you've taken my machine learning class, we talked about kernel smoothers, and the idea is the same. You want to give more weight to the closer neighbors, less weight to those neighbors that are further away. So let's just jump ahead to where we're going to land, and this table shows the weight values that we would give for many different smoothing methods. So the average method that we covered way back in week 1 or 2 was where we just take all of our training data and each observation gets a weight of 1 over big T. All right, so this table is going backwards. Big T is the most recent time period. This would be 1 month ago, 2 months ago, all the way back to the beginning of time. And so with the average method, all observations get the same weight. Now, last week we talked about simple moving averages, and so the moving average forecast of order 4 would simply say we're going to average the 4 most recent values and give no weight to anything that happened prior to that. So you could think about the weights being computed as follows. We give a quarter of the weight to the most recent observation, quarter of the weight to what happened last month, quarter of the weight 2 months ago, quarter of the weight 3 months ago, and then no observation matters. No other observation matters when we're computed a moving average. All right, well, let's go to the complete other extreme, which is the naive method that we covered back in week 1. Remember what naive says. Naive says we're going to give all the weight to the most recent observation, and then we basically ignore everything else. All right, so our forecast is simply the most recent observation, which is equivalent to giving all the weight to the most recent observation. Well, what I said last week was a moving average is kind of a halfway house between the average method and the naive method, because a moving average of order 1 would give us the naive method. It's just average the most recent observation with itself, and you get the moving average. You get the naive method. Likewise, if I take a moving average of order big T, then I get the average method. Well, what we're doing with simple exponential smoothing is we're going to have a parameter that controls how quickly our weights are going to decay. So we want to give more weight to more recent observations and less weight to observations further back. And so it's not a step function the way the moving average is, or naive for that matter. And so we're going to have a parameter alpha that controls this decay. So with very large values of alpha, the weights are going to decay very quickly. So we'll get into exactly how I compute this in a minute, but you're going to see with a large value of alpha like 0.8, we give a whole lot of weight to the first observation, the most recent observation, and then by the time you go 5 observations back, that what happened 5 periods ago basically doesn't count. It would get weight 0.001. Alternatively, I could pick a much smaller value of alpha, and then the weights are a little more evenly distributed. So this month gets weight 0.2, last month 0.16, and you know, when we go 5 periods back, we're still giving it about 8% of the weight. All right, so that's the whole idea. Instead of you know, kind of all or nothing, we give all the weight to a couple recent observations and then nothing beyond that. Simple exponential smoothing is going to let these weights decay gracefully and approach 0 the further back we go. All right, so this alpha is called a smoothing parameter. It's just another example of a smoothing parameter like the moving average order. So if you have an order of 1, you get naive. An order of 4, you get something that's a little bit smoother than 1, not as smooth as what you get if you make that big T. So it's just a different way, but we're going to let the weights decay gradually to 0 instead of this step function that you get with the moving average. All right, so this slide gives us basically everything we need to know about the simple exponential smoothing method. So there's a couple ways that we can define this or think about this. And the method I'm going to start out with is by giving you what's called a smoothing equation. So the smoothing equation is this. My level at time t, and by the way, this level at time t, if we jump ahead here a little bit, is going to be what I'm going to use as my forecast value. So, you know, as a simple example of this, my level at time t for the naive method is just my current value. All right. Well, all right. So my level at time t is going to be a weighted average of 2 things. So the first thing is my new information. So my new information is what just happened at time t. So that's what I've observed at time t versus what I knew before. Okay, so LT minus 1 has a lot of interpretations. One is it's my forecast of, it's what I thought was going to happen at time t. So this would be using all the information I had as of time t minus 1. What do I think is going to happen at time t? So you can think about, we're just averaging what actually happened with what I thought was going to happen. So that's one way to think about this. And a couple other details on this. Alpha is called the smoothing parameter. It has to be between 0 and 1. And so what alpha is really doing is it's saying, how much weight do I give new information versus old information? So what happened prior to time t is all captured in this LT minus 1. So how much information do I want to give, how much weight do I want to give to the new information versus the old information is a way that I like to think about this. L sub 0 we're going to call a starting level. So you got to start somewhere on this, and I'm going to discuss that in a second. Okay, one more really important thing to note about this is it's very easy to update your model when you get new information. So as time moves on, we continually observe new y's. So if y is my sales in time period t, every month I get to observe a new y. So how do I incorporate this new information in my model? Well, the answer with SES is very simple. Just average it. While if you think about a more complicated model, say some machine learning neural network model, you'd have to retrain it every time you got new information. So this is a much simpler model. So this is one of the main virtues of this approach, is the ease that we have in updating our model every time new information comes in. All right, how do we get alpha and our initial level L0? So there's a couple ways that we can do this. The one approach is to simply take the first value of y as your initial level. And so the option initial equals simple does exactly this. Or you could average the first couple values if you'd like. That would be one approach. Another approach is to estimate it with least squares. And so the default option in R, which is called the optimal method, simply minimizes the sum of squared errors. So think of this as the error from the one-step look-ahead forecast. So if I use all the information I had as of time t minus 1 to forecast what's going to happen now, so that's like the error from your forecast squared. So we're just simply going to minimize the sum of squared errors with respect to the two parameters, alpha and my initial level L0. Now, you can specify in R one or both of these. So for example, I could give it an initial level and let R, then R would automatically pick alpha for us. Or I could give neither, and then it does both. So R is very easy to use. Okay, earlier I mentioned there's a couple ways to describe SES. So another way to describe this that's equivalent to this the smoothing equation that I gave up above is what's called the weighted average approach. And so I want to go into some detail about this weighted average approach. And so let's derive this off to the side here. So let's begin by stating my recursive smoothing equation. So my level at time t, remember, is just whatever new information I have at time t with a weight of alpha, plus, well, 1 minus alpha times whatever my level was at time t minus 1. All right, well, let's start with L1, and I'm going to just write it out. So L1 is equal to alpha times whatever my y value is at time 1, and then I have 1 minus alpha times this initial level, L naught. Oops, that should be a times right there. That's a time symbol. All right, well, great. Let's go write out what is L2. Well, using my recursive smoothing equation, this is going to be alpha times y2 plus, well, 1 minus alpha times L1. And so what is L1? This is L1. So I'm going to go drop that in. So we can think of this as alpha y2 plus 1 minus alpha times the quantity in parentheses here, alpha y1 plus 1 minus alpha times my L0. Now I can expand this a bit if I want. This is alpha y2 plus, I'm going to have 1 minus alpha times alpha times y1 plus, well, 1 minus alpha times, that's squared, L naught. And so what we see happening here is that, you know, you could think of me having a 1 minus alpha to the 0 power here. Then I have a 1 minus alpha to the 1 power here, and I have a 1 minus alpha squared power back here. I hope that you're seeing the pattern. Just in case you aren't, let's just write out one more equation here. So this would, using my definition of the smoothing equation, this is going to be alpha times y3 plus 1 minus alpha times L2. And my L2, I just worked really hard to give me this big mess up here. All right, so this is equal to alpha y3 plus, let's just go drop all of this in for L2. That's an arrow. This is going to be, well, alpha times 1 minus alpha times y2 plus, well, I'm going to have 1 minus alpha squared times alpha times y1 plus, going back here, this is going to be 1 minus alpha cubed times my initial level. And so what I'm trying to get at is, you know, my level at time t is going to be some alpha times the sum. We're going to have a 1 minus alpha. This is going to be I equals naught to t. This is going to be 1 minus alpha to the I times y sub t minus I. Okay, so that writes out the sum, and then I've got my initial level as well. So I should probably include that. So plus 1 minus alpha to the t times my initial level. All right. So this is the moving, this is the weighted average version of this. And what I want you to note is we've got, those are my weights. And if you remember a geometric series, so a geometric series looks something like this. S sub t is A plus, let's use the traditional notation AR, plus all the way through AR to the t minus 1. That's called a geometric series. What we have here is a geometric series. my A's are these alphas, and my R's are these 1 minus alpha values. So let A equal alpha, and my R is 1 minus alpha. And what we know is that if we take the limit as t goes to infinity of st, this is equal to A over 1 minus R. So that's a really famous formula that you would have gotten in your, when you covered sequences and series back in calculus. And so the sum of this would be, so the sum of my weights would be alpha all over 1 minus alpha. Well, this is just alpha over, the ones go away, alpha, which is 1. So my weights sum to 1 with this geometric series. So this is a really important trick. This geometric series is probably the most important series in all of mathematics, and it gets used a lot in time series. We're going to see it creeping up very often as we cover additional methods. All right. So that's what I've just said here. So note the sums approach a weight of 1. Next, I'd like to take us through an example, and I have to first admit it's kind of hard to find a marketing example that uses just the simple exponential smoothing. And the reason for this is usually in marketing, our data sets have trends and or seasonality. So almost always we have a trend or a seasonality to deal with, and I couldn't find a data set in marketing that didn't have a trend or seasonality. So I've taken the cow temperature example from R, or I guess we're measuring a cow's temperature over time. And this one is an example of a series that does not have any seasonality. So if you want to read about this data set, you can just get some help on it. And so it's the daily morning temperature of a cow measured for 75 consecutive mornings. So you have my R code in the packet, but I thought I would just do this live in R. So to get a simple exponential smoothing model, the forecast library, make sure you've loaded the forecast library, gives us a function SES. And so this is an extremely simple wrapper that uses a more general function that we're going to learn about in a later video. And all we do is we give it the time series, the number of forecasts we want, what sort of prediction intervals do we want, how do we want to initialize the value. If I want to give it an alpha, I can. This lambda is a box-Cox lambda, so the function does that, and it also does bias adjustments if I want. Well, let's go take a look at this cow temperature data. I should probably show you what it looks like first. So let's get an auto plot of cow temp. And so what we see is that there's a lot of fluctuation. I don't really see any strong trend. Maybe it's decreasing a little bit over time. So I'm going to go fit a simple exponential smoothing model, and this h equals 5 means give me forecasts for the next 5 days. So if I plot the fitted object, I get the original time series plus the forecasts. So one thing to note about these forecasts is that they are constant over time. So the forecast is not moving. And the reason for that, going back to the course packet, is this forecast equation. So my forecast h periods into the future is just the current level and that never changes as h increases because there is no trend and there is no seasonality to account for. All right, well, if I display the fitted object, what I get are the forecasts with the 80 and the 95% confidence levels, and those are shown in the dark blue, that be the 80% PI, and the 95% in the light blue. The fitted object has a whole lot of components. Fit dollar model I find extremely useful, and so what we get here is our estimate. So this is the least squares estimate of the best alpha, and you can see it's about 0.2. It also estimated the initial state to be about 0.63. Then let's carry on. The fit dollar mean gives me the forecast values, so 5 periods into the future. Fit dollar level just tells me the PIs. Fit dollar X, gives another copy of the original data set. Lower and upper give me the prediction intervals for the forecasted values. The fitted component of this list gives me the values for all of the 75 training cases. Method gives me the name of the smoothing method, in this case, simple exponential smoothing. Our series is cow temperature. And the residuals give me, well, fit dollar $X minus fit dollar fitted. So let's just go type that in. And so what you'll see is you get exactly the same values as fit dollar residuals. So that's where that's coming from. I like to do these things in Excel by hand once, just to make sure I know what's going on. So to make my life really simple, we're going to pick alpha to be 0.2, and we're going to set the initial values to be, just use the simple one as opposed to estimating it from the data. So we get our estimated values, and if I display the fit, I get the point forecast by default for the next 10 periods. Well, where does this come from? So let's go estimate this in Excel. So here we are in Excel. I've added a row for my alpha value. So here I just set it equal to what I set it to in R. Then I also added a row for time period 0, which since I chose the simple method of initialization, I'm just going to set that equal to the first value. Now, the way we make our 1 period look ahead forecasts, or my level at time t, is going to be the level alpha. So the value alpha here is $1 times the new information plus, 1 minus $1, in this case that'd be 0.8, times the previous level. So I've just set up my recursive relationship, and I can easily copy this down. So where is this value coming from? Well, I give 20% of the weight to the new value, which is 70, and I give 80% of the weight to the previous level, which is 60. So this would be 0.2 times 70 plus 0.8 times 60, and that's where 62 is coming from. Let's just go see if that's what R got, and you'll see R got exactly that. The next value would be 60.4, and that's exactly what Excel gave us. Where's that coming from? Well, I give 20% to the new information, 80% of the weight to the previous level, which is 62, and so that's where that's coming from. If I scan forward all the way to the bottom, you're going to see my final level is 48.88, and that's going to be the value of my future forecast. So 48.88 will be my best prediction of what's going to happen in the future. All right, so I think having done this in Excel, I claim to kind of understand what's going on. All right, the last thing I want to do with this example is to have a test and a training set and compare a few methods. So you're going to see we have a time series of length 75. I just decided to use the first 50 observations as a training set. We'll use the last 25 as a test set. So let's go fit a model with R choosing the alpha it wants. And so you can see the alpha it chooses is about 0.2. Actually, since I'm only using the first 50 observations, it chooses a slightly different alpha of 0.1976. Earlier it was slightly more than 0.2. But what we're seeing is that this optimal amount of weight is about 0.2. And then just for fun, let's go take the naive method, which would give all the weight to the current observation. And I chose a few more values of alpha just for contrast. So we'll use an alpha of 0.5, where we're smoothing a bit more than the naive method, but not as much as the optimal one. Then I chose an alpha of 0.05, which should be over smoothing. It's going to start approaching the average method. So let's go take a look at how I do on the test set. So here are these four sets of predicted values. What I would be doing in real life would be comparing the test set RMSE values. And so what you'll see is the value that R chose gives me the smallest RMSE value. So naive is not doing very well. The RMSE is more than double. With an alpha of 0.5, I'm smoothing a bit, but not enough. And so you'll see my RMSE is higher. And when you give an alpha of 0.05, you've over smoothed. And so my test set RMSE values are showing that, as well as the training set RMSE values are also showing that. If I wanted to use mean absolute error, I'd be coming to the exact same conclusions. My test set MAE is lowest. I think there's a lot of benefit to looking at the forecasts. So let's go do that. So what you'll see is I've given us the original data, the fitted data, and then the forecasts. And so this is the optimal set of predictions. Let's regenerate that so it maybe fills the screen a bit more. And so the red line is what I get with this optimal level of smoothing. And then the dark blue line here is going to be my my fitted values, my forecasts for the future, the last 25 test set values. Let's go see what naive does. And so you'll see naive is just, it's a copy of the original data moved one period forward. And so the red line is exactly the black line moved one period forward. And we're following every wiggle in the data. We're just one period behind with the naive method. Let's contrast this with the 0.5. And so what you're going to see is that it's a very wiggly estimate. The red line is very wiggly, but not quite as wiggly as the naive method because we're doing some smoothing. Now, if I compare that with, this is where I chose a value of 0.05. Here I've over smoothed, so I'm not really capturing a lot of, the temperature went down here, and I'm not capturing that at all. My smoother is not reacting to that very quickly. It takes a long time for that to drop because I'm giving so little weight to the current value. If you want, we could compare all of these on one plot. And so I think this makes it pretty clear. There's a lot going on in this plot, but the purple is the naive that follows every wiggle in the data. The blue one you see is smoothed a bit more, but it has a lot of wiggles. The optimal one is this green one, and it kind of nicely captures what's going on. It tracks any changes that are happening without waiting too long whereas you can see the red one just waits too long. It's just too slow to react to any changes in this time series. All right, one more thing, I should have fitted in ACF. So let's just go look at an ACF. This is one of the first things you should always look at when you look at your data. And so what we're seeing here is there are some autocorrelations. And so that's just a signal that there's something cyclical going on here. And our smoothers taking advantage of that. The SES is taking advantage of the fact that there's a correlation between the observations. All right, so that's about everything you need to know for SES. Next video, we're going to talk about how do we incorporate a trend.